Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion. We have been looking at Chapter 9 in A Student's Guide Through the Great Physics Texts, Volume 2. This is called the mean speed theorem. And in this chapter, what Galileo is doing is explaining a technique for computing the distance that an object moves while it's undergoing uniformly accelerated motion. That is, when it's falling. If you jump ahead to figure 9.1, we have been talking about a specific technique called the mean speed theorem. Let me remind you what it says. It says that if you want to know how far an object falls in a given time period, given in this diagram by line segment AB, well, it starts out at 0 speed and it ends with a speed given by the length of line segment EB. Well, if you want to find out how far it falls, there's an easier calculation to do. All you need to do is find out the mean speed, or the average speed that that object is falling at. That would be given by the line segment FB, or BF. And if you consider that other object that's traveling at that mean speed, BF, for the same amount of time, AB, you can just find the distance that falls by multiplying BF by AB. That is the speed times the time. In particular, what you're doing is you're finding the rectangle area, the area of a rectangle ABFG. That's an easy calculation to do. I use the example of traveling at 60 miles per hour for 1 hour. 60 miles per hour would be denoted by the line segment BF, 1 hour by the line segment AB. You find the area, which would be 60 miles. So that's the way you calculate the distance moved. Now here's the claim, is that the object that's undergoing uniform acceleration, that is starting out at 0 speed and ending at speed BE, would travel the exact same distance as the object going at the uniform speed for the same amount of time. Now, how is this clear from this diagram? That is what Galileo is talking about in the paragraph after Theorem 1, Proposition 1, which is the mean speed theorem. Let's talk about this in a little more detail. How does he know this? Well, during the first half of the fall, let's say the time period that goes between A and halfway to B, during that half the fall, notice that if it's falling, it's going a bit slower than the uniformly moving object. That is, it starts out at 0 speed, whereas the uniformly moving object would be moving at speed given by line segment AG. So it starts out going slower. Okay, so let's write that down. So during the first half of the fall, the falling object is traveling more slowly than the second uniformly moving object. That is up until the halfway point. By the halfway point, this point right here, it will be moving at the exact same speed as the uniformly moving object. Okay? So, if the distance traveled by the uniformly moving object was computed as the area of 4 little rectangles. So these little rectangles that he draws here, each of them, so the uniformly moving object will be traveling a distance given by the area of those 4 little rectangles. Then the distance traveled by the uniformly accelerating object is just half of this distance. Right? So in the 4 rectangles, if we were to draw it like this, that would represent the distance traveled by the uniformly moving object. And half of this, that is the area of that triangle, this would be the uniformly accelerating object. This is probably obvious to you also, just from the area of a triangle is 1/2 the base times the height, whereas the area of the rectangle is the base times the height. So clearly the distance traveled during the first half of the fall is going to be half as far for the uniformly accelerating object compared to the uniformly moving object. Hopefully that makes sense. Well, what about during the second half of the fall? So during the second half of the fall, the uniformly accelerating object is traveling on average faster than the uniformly moving object. Right? Because it starts out the second half of the fall with the same speed, but by the end it's traveling faster, in fact twice as fast. So we can see that if the distance traveled by the uniformly moving object is, once again, 4 little rectangles, then the distance traveled by the uniformly accelerating object is what? 6 little rectangles. Right? So if I draw this once again over here, during the second half of the fall, the distance traveled by the uniformly object is once again 4 rectangles, but the distance traveled by the uniformly accelerating object is once again those 4, but then plus half of another 4 rectangles. So that would be a distance of 4, and that would be a distance of 6, right? 6 rectangles, 4 rectangles, and this would be 6 rectangles. You know, we're measuring distance in rectangles because it's a distance, it's a speed times a time. Okay? And so finally, if it moved during the first half of the fall 2 rectangles less than the uniformly moving object, and during the second half of the fall it's moving 2 rectangles more than the distance moved by the uniformly moving object, then, or therefore, the uniformly accelerating object travels overall the exact same distance as the uniformly moving object during the entire time of fall. That is the time AB. Hopefully that's clear, and that is precisely what Galileo is saying. That's how he's employing this mean speed theorem strategy. Okay, so we now have a strategy for finding out how far a falling object descends in a given amount of time. The strategy is just find the mean speed or the average speed and then calculate how far a uniformly moving object would travel during that time interval. So let's do a couple of examples. So let's suppose, I'm just going to say these, I'm not going to write these down. See if you can figure out how to calculate these. Suppose that some object is dropped. And let's suppose we'll use the International System of Units and the known acceleration of gravity of about 10 meters per second squared. That is, it gains 10 meters per second of speed for every second it falls. So here's my question. How far will a dropped object fall in exactly 1 second? Okay, how do you answer this question? Well, you need to find how far another object would fall that's traveling at the mean speed. If you drop an object, it starts out with a speed of 0. At the end of 1 second, if it's undergoing an acceleration of 10 meters per second, At the end of the first second, it will be falling at a speed of 10 meters per second. Now, how far does it move? Well, you take the average of that. The average of 0 meters per second and 10 meters per second is 5 meters per second. So all we need to do is ask how far an object moving at 5 meters per second for the whole 1 second would travel. 5 meters per second times 1 second is 5 meters. Therefore, the object falls 5 meters. Let me ask a harder question. Let's suppose we wanted to find out how far an object falls when it falls for 2 seconds. Well, the same strategy applies. At the beginning of the fall, it's going at 0 meters per second at the moment you drop it. At the end of 2 seconds, it will have gained 20 meters per second of speed. 10 meters per second during the first second, 10 meters per second during the second second, so it will be going at 20 meters per second. Well, how far does it fall? We take the mean of those. That is 0 plus 20 divided by 2 would be a mean speed of 10 meters per second. If an object travels 10 meters per second for 2 seconds, that would travel a total of 20 meters. Therefore, the dropped object falls 20 meters in 2 seconds. So it falls 5 meters during the first second and a total of 20 meters over 2 seconds. So subtracting those, you could figure out how far it fell during the second second, and that would be 15 meters. What about during 3 seconds of fall? How far would it fall? Well, it starts out at 0. After 3 seconds, it's falling at 30 meters per second. And so the mean speed would be 15 meters per second. Moving an object uniformly moving at 15 meters per second for 3 seconds would just move 45 meters. So a dropped object will fall 45 meters in 3 seconds. Notice here that during the first second, it falls 5 meters. During the second second, it falls 15 meters. And during the third second, if you do a calculation, you'll find that it falls 25 meters. So it falls 5 during the first, 15 during the second, 25 during the third. And notice the ratio of those numbers, 5 to 15 to 25, is a ratio of 1 to 3 to 5. If you keep going, it's 1 to 3 to 5 to 7 to 9 and so on. And this is precisely what Galileo claimed at the beginning of this chapter when he said that the distances fallen in subsequent moments of time has a ratio of 1 to 3 to 5 to 7, or the ratio of the odd numbers beginning at unity.